Today we are going to discuss on a step circuit failure experienced during fourth campaign of one of the blast furnace, which ran from 2003 to 2014. Specifically, we will focus on the correction measures used to manage these failures and key lesson we can apply to our own operation. So, from that point of view, this presentation is very important. Let us see what is the furnace background and the stave system. So let's have a focus on, we can say, a sort of a overview on its stave system. First, some background on the furnace. So the fourth campaign began in October 2003 after a major reline. The old plate cooled design was replaced with a modern system of 6 row of copper stave and 5 row of cast iron stave. Now this upgrade increased the furnace working volume by 11%. The copper staves are arranged in row M1, B1 and B2 in the Bosch, S1 in the Bailey and S2 and S3 in the lower stack. There are 264 copper staves in total. For protection, most staves had 35 reeps with poured alumina refractory between them. A key difference which will come back to is that the top row of copper stave S3 used silent carbide SiC brick inserts instead of alumina castable. Now coming to the early warning signs and wear measurement. The first sign of trouble appeared in 2009, 6 years into the campaign. The team noticed the failure of thermocouple in B2 stave row. As you can see that if once this thermocouple went away, it gives a lot of alarming signal on a potential damage. These thermocouples are set 20 back from the hot face. So their failure was a clear indicator that significant rewear has already occurred. To understand the extent of the problem, the team used several measurement techniques. They inserted probe hook through the bridge thermocouple valves and took core sample to map wear pattern. They also used ultrasound measurement through the water circuit, which proved highly accurate for the S2 stave. This method shows typical wear rates between 0.25 and 0.75 millimeters per month, and which is supposed to be a high. Now, the first actual stave circuit failure occurred in October 2011 on the B2 row, followed by S2 stave failure just 4 months later. As more circuit failed, two critical pattern emerged. First, on both B2 and S2 stave failure always started in center circuits and then progressed to outer circuits over time. Second, the failure were regional, concentrating in specific areas around the furnace circumference. So these were the both are the very important learning point for our furnaces also. So with circuit failing, the primary operational goal becomes protecting the furnace shell by keeping temperature below 250 degrees Celsius. This was critical to prevent failure of weaker 5 by 8-inch seal plates on abandoned cell opening. Now the team developed different remediation strategy for each affected stave row. For B2 stave in the upper Bosch, they first tried inserting corrugated hoses, but these had limited cooling effect and was abandoned. The most effective solution was using nitrogen with a water mist to cool the failed circuit, which was automatically triggered by high temperature. Additionally, they strategically blanked tuyers below the highest wear area. As you can see in many our furnaces also. So this promoted the formation of a protective scab, successfully slowing down wear in that region. For the S2 stave in the lower stack, they had a unique advantage: old cooling plate opening in the shell. This allows them to cut through the failed section of a stave and insert a new cooling plate directly into the furnace. The remaining good part of the stave circuit was then put back on the water. This brilliant fix prolonged the life of outer circuit on those staves by additional 24 months. And this is also a way out to learn from this case study that in our cases also how to meet such contingency situation. Now, coming to the by the third year of the dealing with this issue, the situation escalated dramatically, and this is also a signal for day-to-day operation of common furnaces that once such type of damage occur, it's unstopped, even though we take a lot of precautionary measure. The failure frequency increased fivefold, and the S1 Bailey staves also started to fail. Mainly, individual nitrogen cards for each failed circuit becomes impossible. To solve this, the team engineered supercoolers, which were consolidated unit that could supply nitrogen and water mix to multiple circuits and be controlled remotely. Over a 32-month period, a total of 84 circuits failed, and 46, 46 of them were managed with this nitrogen based cooling system. Continuous monitoring with infrared camera was also installed in high risk area to watch shell temperature closely. After the furnace campaign ended, a post-mortem investigation revealed two primary root causes for the failure. First, cell geometry. A 3D scan revealed an inward bulge and out of roundness in the shell from damage that occurred in 1990. The location of the highest stave failure in the Bosch and Bailey correlated directly with this cell irregularity. Second, refractory performance. The finding here was stark. The silica carbide brick insert in the S3 stave performed exceptionally well. Most brick is still intact, protecting the stave ribs. In contrast, the alumina castable used in all the other stave row was completely gone. This is critical lesson in material selection. So, what are the main takeaways for this campaign? The most important success is that the combination of these remedial measures or techniques successfully and safely managed the furnace for 32 months after the first failure. No stave were ever completely lost and no new damage was done to the furnace shell. The key lesson for us are one. The first one is cell integrity is paramount. Pre-existing geometric issues can create hot spot and uneven wear pattern. Point number two, material selection matters. Silica carbide brick insert provided far superior protection to the stave ribs compared to the standard alumina castable in high wear zone. Point number three, a protective and adaptive approach using tools like nitrogen based cooling, targeted plate installation, and continuous monitoring can effectively extend a furnace campaign even with significant equipment degradation.